In our motivation video, we introduced the fact that airplane wings, or any beam or shaft for that matter, can twist as well as bend. Torsion can be defined as the twisting of a member when it is loaded by some torque and occurs in all sorts of engineering applications. Let's investigate some of the math behind torsion. Suppose we had a circular shaft fixed at one end, and along the length of the shaft, we will take our marker and draw a line. When we apply a torque to the shaft will want to twist, and we can see that the marker line we drew before will move accordingly. If we look at the circular shaft more head-on, let's denote the angle between the original marked line we drew before torsion and the new position of the marked line after torsion. This angle, phi, is known as the angle of twist. Now, going back to our side view, let's denote the direction of the shaft's length to be along the x-axis. It turns out that the angle of twist, phi, is actually a function of x. To see this, imagine that we still applied the same amount of torque, but the shaft was much shorter. Watch, as the shaft shrinks in length, the angle of twist must be smaller, given that the marked lines we drew before and after applying the torque are closer together. Now, let's consider an infinitesimally small strip on our shaft and take our marker to make lines AB and CD. When a torque is applied, the free end rotates, and the lines AB and CD are no longer perpendicular to the cross section as they once were. This sort of distortion is indicative of a shear strain. Thus, it turns out pure torsion of a bar is associated with a state of pure shear. Now, let's do some geometry. Let's denote the angle between these two lines, AB and AB prime, to be gamma. Therefore, by some simple geometry, the tangent of gamma is equal to the distance BB prime over AB. However, we'll make the small angle assumption that tan of gamma is very, very close to gamma, given that we assume that gamma to be very small. From the figure, we can see that B prime is equal to R d phi by the arc length formula for an infinitesimally small phi. Therefore, gamma is equal to R d phi over dx. This is great. We have a formula for shear strain on a shaft. But what about the shear stress? Remember, from last video, Hooke's law for shear stress is that tau is equal to G times gamma. Taking our equation for strain and plugging it in, we get something that looks like this. Now, via higher mathematics, it can be shown that this equation simplifies in a pure state of shear to G times R times phi over L, where R is the radius of the shaft, phi is the angle of twist, and L is the length of the shaft. Again, some more steps in mathematics that we have left out for simplicity means that this new equation is also equal to T times R over J, where T is the applied torque. J is known as the polar moment of area, and it is calculated for each cross-sectional shape of the shaft in question. J determines which geometries have higher resistance to twisting. Going back to the equation we arrived at, some algebra yields the following. Phi, the angle of twist, is equal to the applied torque times the length over the polar moment of area times the shear modulus. Though it might not seem like it, there's a lot of use for this formula. Remember last video when we talked about normal strains and stresses and how the modulus of elasticity, E, could be calculated by a tensile test? This equation we have here is the governing equation for a torsion test. Given a shaft with a known length and a polar moment of area, by varying the amount of applied torque and measuring the response of the angle of twist, one can determine the shear modulus G. That's all for now. Join us next time when we delve into the topic of beams and how they bend.